John Dalton was an intelligent, modest man, and he had one very British passion: the weather. He was born here in the Lake District in 1766. He was so clever that as a young boy, just 12 years old, he was already teaching other kids at a school that he set up. Walking home, he loved watching the weather system sweeping across the fells. He was so obsessed that he kept a meteorological diary for 57 years. And every single day, come rain or shine, he entered his precise observations, 200,000 of them. Dalton was a quiet, retiring man with modest habits. He was a lifelong bachelor, with not much in the way of a social life. His only recreation was a game of bowls once a week, every Thursday afternoon. He was certainly a creature of habit, and he might sound a bit dull. But actually, Dalton was an avid reader and a deep thinker. Underneath his mild-mannered exterior, his head was teeming with radical ideas. Now, scientists had recently discovered something very important about the way elements combine to form compounds. When they do so, they always combine in the same proportions. So Dalton would have known that common or garden table salt, sodium chloride, is always made up of 1 part sodium and 1 part chlorine. So it doesn't matter whether the salt comes from Salt Lake City or Siberia. It's always in the same proportion by weight every time. Dalton reckoned for this to happen, each element had to be made up of its own unique building blocks, what he called ultimate particles, atoms. It was a blinding illumination, completely left field. Everything, he suggested, the entire universe, was made up of infinitesimally small particles. The Greeks had hit on the idea of the atom 2,000 years earlier, but abandoned it. Now, Dalton took up the baton with his own theory of matter. What Dalton was describing was revolutionary. He had struck on the foundations of atomic theory, foreshadowing research that wouldn't be proved until over a century later. He proposed that there are as many kinds of atoms as there are elements. And just as each element is different, so each element's atom has a different weight, a unique atomic weight. Every element has its own signature atomic weight, whether it be a solid, a liquid, or even a gas. These 3 balloons are each filled with a different gas. Now, they're roughly the same size, so they should each have about the same number of atoms in. Dalton reckoned that different atoms have different atomic weights, so these 3 balloons should each weigh different amounts. So this red balloon is filled with helium gas, and if I release it, it floats. Helium is very light. This second balloon is filled with argon gas, and if I release it, it sinks slowly. Argon's heavier than helium. The third balloon is filled with krypton gas, and if I let it go, it falls like a stone. So Dalton was on the right lines. Different atoms of different elements have different weights. Based on this theory, and working completely alone, Dalton made one of the first attempts to impose some order on the unruly world of the elements. This wonderfully mystical set of symbols is Dalton's lineup of the elements, arranged by weight. Now, there are some elements here that I don't even recognize, but he does start with hydrogen at 1. Then you go down to oxygen at 7, and then all the way down to mercury at 167. As it turned out, Dalton didn't get all of his weights right, but he'd made a huge theoretical leap, working purely from his mind's eye. 200 years ago, John Dalton was using his imagination as a microscope. But today, we have the technology to see the contours of individual atoms with this scanning, tunneling microscope. It's not like a normal microscope because it doesn't use light. Atoms are less than 1/millionth of a millimeter across, which is smaller than the wavelength of visible light. This microscope uses electrons to scan across the surface of materials, picking out individual atoms. The images it produces are striking. These are atoms of shining silicon. These are carbon atoms. This is what gold atoms look like. And these are atoms of copper. Copper is a lustrous metal, essential for life. It fueled the move out of the Stone Age into the Bronze Age. Copper nuggets can be found on the Earth's surface, but it usually needs to be extracted from ores. And copper compounds run in the veins of some animals. The blood of the octopus is blue, along with snails and spiders. John Dalton's idea in the early 1800s that elements had different atomic weights was dismissed by many scientists.